Hello, I hope everyone is having a good week. We are on week 3 of the class, week 8, my mind's somewhere else, of the class so far. We're making good progress. So right now we're kind of at a pivotal point. So we're kind of coming up to spring break, midterms, things like that. So let's talk about that here. So in the syllabus, I have week 8 and week 9, and theoretically this is midterm week, but actually next week's midterm week. So these things are interchangeable. Basically, I'm going to give you this lecture for this week and next week. In theory, this lecture for this week, 3-4. Today's 3-4, so this is a lecture for this week. And then next week is spring break or the midterm. You have a couple days to do the midterm. I put a video up on the midterm. It's not difficult. Just follow the video. There's 2 parts to it. Please make sure you do both parts of the midterm. But yeah, this lecture, the homework, everything else, this is the last lecture you're going to have until I think it's 317, 318. So there's not going to be a whole lot more added on. So just kind of keep that in mind. So this lecture is, however you want to do it. If you want to watch it on 311, that's fine. If you want to watch it this week, that's fine. Whatever you kind of want to do, however you want to manage your time is completely acceptable. Next week there will not be a lecture. Neither one of these weeks. There's no discussion, so you don't have to worry about that. So no discussions. So I think we're in a good spot. So we're going to attack. I just had that book around. We're going to attack this book a little bit. This book's kind of good and bad. There's a lot of things I like about this book and a lot of things I don't like. But more than anything else, it provides a really good fundamental understanding of models like BERT and GPTs. It kind of talks about autoregressors, things like this that I think are kind of vital to understand. Now, it does talk about things that aren't always necessarily relevant, so I'm going to try to skip that. In theory, this is going to be the only lecture that kind of covers that book, except for maybe one caveat. There is possibly another lecture I'd like to do somewhere on vector databases, vector searches, and actually having you guys do more than word2vec. Actually having you store some data in a vector database or looking things up in a vector database. Just a little bit more playing with vectors because they're such a vital concept to this topic. But other than that, this is just kind of the book on that. So it's funny because I think somehow through the process, I took this as you're driving out of Las Vegas to California. When you hit state line, that's those mountains over there. But remember that chat GPT and large language models and a lot of what we do, the purpose of this technology is not to make our life more miserable. It's not to make our life more unhappy, but it's to make our lives happier. It's to simplify our lives. And if you kind of take that approach to GPTs, to large language models, to a lot of what the new technology is, you'll be happier. So yes, you can totally use GPTs to cheat. And nobody can deny that, okay? But I'm not saying you're cheating yourself, you're cheating others. I don't believe in any of that. But that's not really the goal of a GPT. That's not really the goal of a large language model. Large language models and Copilot and these other programs are designed to make you enjoy what you do more. If you're going to kind of enjoy what you do more, you'll maybe get more happiness out of life and more fulfillment. So when you use LLMs, when you use a lot of these machine learning models, remember that at least in my mind, in some part, their goal is to help humanity, to make the world a better place. Hopefully that makes a little bit of sense. Okay, so really, where did large language models come from? And there were large language models before this, but there was a paper, and I put it in the extra credit section, basically on how transformers can attend to or can focus on certain parts of I guess a word, a vector, a sentence that can relate to others, and the distance. And it's hard because, again, we're not a lot of computer scientists. I don't want to really dig into the weeds. But if we look at the stock market, that's a really easy thing that we can all make reference to, or cars, or anything else. when do you draw the line between an old version and a new version, or an old CEO and a new CEO? So if I look at, I don't know, Ford stock or Chevy stock or GE stock, let's say GE, because maybe it's been around for 100 years. Well, and I say over the last 100 years, GE has returned my money 10 times over, 10x increase. Now I look at that a little bit more in detail. The first 9x increases were 80 years ago. In the last 20 years, there really hasn't been much. So as an investor, I would be able to see that very clearly. Hey, if I invested in GE 100 years ago, I would have made a lot of money. But if I invested it 20 years ago, I wouldn't. This type of pattern detection is harder to do in computers, okay? Well, that's kind of what self-attention is. The ability to say, hey, this word's related to this strongly, or this word's related to this idea strongly, or not strongly at all, and kind of building those relationships in our mind. We look at it and we say, the CEO here made X, but it had no bearing on the next two CEOs. We can look at the same thing with presidents of the United States. Hey, this president made these laws and it had this effect, but we're not going to go back and look at, I don't know, Lincoln and see what his ideas on, I don't know, healthcare or privacy was, because they just don't match up. So a lot of times when older models work, they kind of try to capture everything. And it didn't work really that well. So that's why we have short, long-term memory. That's why we have self-attention. We have a lot of ways to kind of focus in on what is important and what's not important. And this paper by Google is Attention's All You Need. I think, I don't even know if I put it in there, was one of the pivotal moments of that. Not only that, it also kind of changed the way that training could be scaled up, making training much different. And yeah, there's that. So let's keep going. Great paper. Now, they talk about terms in this book a little bit, and they're slightly different than maybe some of the terms that we've used. So I just kind of want to identify the terms. So they use the word token. And token is the smallest unit of semantic meaning. So the shortest thing that can have meaning. So remember, that could be a really big word. It could be a combination of words, but it has some type of meaning at the end of it. So maybe the might not have meaning, but is might have meaning. So it is how certain units, that's the word I tend to use, certain units have meaning in conjunction with other units. So, what is the smallest way you can break something down? Okay, so that's how they kind of define tokens. Slightly different than the way we define tokens in the past in traditional NLP. In the past we kind of defined tokens as maybe a whole word or part of the whole word. So now this book goes into a good amount of detail about autoencoding and autoregressive models. I know we talked a little bit about BERT when we did BERT topic, but at the end of the day, BERT topic is a bidirectional model, meaning that it can grasp the contents before and after a given token. So you have a token, you have a unit, and you have something before and you have something after. So BERT has that's part of what makes BERT so strong, is that before and after a token. Now, BERT is kind of trained by, and I think there's pictures in the book, if not you can Google it. You'll give it a sentence and you block out a word. And you try to figure out, hey, what is the best fit word in there? Mask language modeling. Did I even put that in there? Oh yeah, but unmasked tokens. So that's all it really is. So that is kind of how BERT is trained. And it's kind of how, we're trained. Sometimes we use wrong words and people correct us and we fix it. And, you find the best word for the best sentence. Okay? So that's kind of what masked language modeling is. Masking some of the input tokens based on the surrounding context and see if we can understand the sentence, understand the context of it. Now the autoregressive, and that's how BERT works. So now there's an autoregressive model. This is how OpenAI, ChatGPT works. Okay, it generates text by predicting the next tokens in a sequence on basically the previous sequence without any knowledge of upcoming tokens. It's kind of different. So it's more forward movement of context, more forward. I don't want to use the word forward thinking, but more forward token. Okay. Remember, its job is not necessarily to predict what's masked. Its job is to predict the next sequence of tokens. The quick brown fox jumped over the lazy dog versus the quick brown blank jumped over the lazy dog. So there's kind of different approach on it. And if you remember what a regression is we're basically pitting a bias and trying to make a line between multiple points. So you guys understand that. Generate text by predicting next tokens. Okay, also there's a T5. I just slipped my mind what T5 is, but T5 model is kind of like a combination, a hybrid model between BERT and a GPT model, between an autoencoding, maybe a little more specific, between an autoencoding model and an autoregressive model, because each model has pros and cons. Okay, the GPT provides one-way context. It provides forward-only context. BERT provides bidirectional context. So the T5 kind of hybrid merges both of these. So let's see what else we have. Okay, so encoder and decoder. So encoder tasked with understanding. Okay, so let's talk. Okay, an encoder. At the end of the day, word to vec is very simple. It's an encoder. Okay, but generally with LLMs, our encoders are a little bit more complex, or a little bit more dimensional. Okay, so the encoder's role is basically just to take that text and somehow convert it to a vector, or convert it to numbers that the machine can understand. The encoders where you see the attention mechanism, we use the self-attention to determine the context of each word in a sequence. Where word2vec doesn't really understand the context and the relationship per se, an LLM encoder, a couple different types of encoders do understand the context a little bit better. Let's see. Now, so an encoder takes what you type, what you say, and converts it into vector or vectors, so the machine can understand what you're asking mathematically through numbers. Okay. So once we have that, so now we have data going into the machine. Machine does its magic, uses AI and weights and biases. Then it has to take that number that it generates out, and that has to take that number and kind of decode it into English. Decoder. So decoder basically specializes in generating text by like kind of predicting the next sequence, the next token, I guess, next sentence on the context provided by the encoder or the previous set of tokens or something. Okay, so decoders are very suitable. They're used for text generation. They're used for translations. They're used for just everything. Okay, so its job is basically to generate text. An encoder is to take text and make it into a vector. Okay, and you'll see models and pictures. You don't really need to worry about that. As long as you get the kind of the big picture ideas, that is what's important. Because again, I think you're going to see a lot of these integrated into a lot more programs. We're seeing Microsoft Windows Copilot and Copilot into Visual Studio, and Adobe has generative AI, and so a lot of programs are adding a lot of these LLMs and transformer-like tools. So we have to have a fundamental understanding of these tools. So your book talks about training or pre-training. I'm not really sure what they call it. But training is basically where, let's say we take an Encyclopedia Britannica or Wikipedia, or they talk about a corpus of a bunch of authors that are in English, have a minimum of 2,000 words, and basically you train these models on it. This training is very computationally expensive. It takes a long time. You need a lot of computers, And a lot of computers cost a lot of money, and it takes a lot of time, and it eats up a lot of energy, and it's just an expensive process, okay? However, once we train a model, we can fine tune it, we can update it. We don't have to destroy everything and redo it again. Let me give you an example of that. The best way, the way I always think about this, the way it's always just kind of clicked in my head, is to learn Python or learn Ruby or learn SQL is a nightmare. Learning a programming language is no easy task. I don't care what language it is, Rust, anything, it's not easy. Okay, so you spend a year really kind of understanding Python and getting understanding arrays and private classes and public classes and all different types of things, and it's a lot of work. I mean, you spend 40 hours a week learning Python, you become good at it. Now, moving to another language from Python, for the most part, is relatively easy because you have the fundamental knowledge of data types. You have the fundamental knowledge of objects. So moving to another language is much, much, much easier. Okay? So that is how LLMs basically grew or grow. They did training. They did a lot of training. Then they basically fine-tune their models. And also, there are certain LLMs that are specialized to do certain tasks. There's legal LLMs that are focused on legal domains, lawyers and stuff like that. There is, I think it's BERT, or BioGPT, which is focused on the biology and PubMed. There's I think a PubMed GPT. So there's all these specialized GPTs. There are GPTs to do translations. There's GPTs to do, or LLMs too. I mean, it doesn't really matter. There's LLMs that do SQL. So basically what happens is I train a large language model on Wikipedia and a bunch of books, and it understands words and it understands context. That's great, but it doesn't understand SQL. So then I take a lot of SQL books, I take a lot of SQL code, I take a lot of SQL and fine-tune that model much easier than I do starting from the ground up. So that's a process of fine-tuning. With specifically enhancing its accuracy and effectiveness for a particular task. It requires much less data than training a model from scratch. So I guess that's that. So again, like I said, I'm not trying to make this a hard lesson. I just want to cover some of the basics. I want to give you guys some time to work on your homework, work on everything you need to, and work on the midterm, work on your other midterms, and do good in all your classes. So an embedding is a mathematical representation of a phrase, tokens, in a higher dimensional space. They're important for NLPs because they allow the model to understand the semantic meaning and relationship of words, sentences, in ways that capture their contextual nuances. But if you really look at word-to-vec, it just kind of captures a word without a lot of understanding of what that word is. Embeddings are bigger picture word-to-vec. Embeddings are larger ideas. But embedding basically captures the context, the dynamicness, the meaning of the word in relationship to other words around it. Okay. The two main types of embedding, there's token embedding and positional or persistent embedding. I'm not going to go a whole ton in detail about that. When I talk about higher dimensional space, I'm just talking about more dimensions, more columns, more things that you'd use PCA or these other like T-sign to reduce the dimensionalities of it. Okay. That's basically all embedding is. If you understand that embedding is basically just a vector of a word or sentence and its relations, then you're good. So how LLMs have changed some of the things is in the past we did keyword searches. So you remember the inverse document frequency, IDF. So IDF is the idea that, hey, if we have a document, we can look for certain words, and in theory, maybe the more rare a word is, the more less it occurs, the more value it might have. that might be true or it might not be true. We're looking at maybe something in biology, and it might just have, might just appear once or twice. Hey, this thing happens, blah, 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 but on the off chance this is what happens. I got a check in the mail. I've gotten 2 checks this year, but I got 1 check just last week, and my name was spelled wrong. It was missing a letter. So if you were to put that into some type of IDF, inverse document frequency, it might say, hey, this is a really important word, because it only happens once. Out of 1,000 checks in my life, this one might be really important because it's only appears once. No. Semantic search, how LLMs work, they understand more of the context. They understand kind of what you're looking for. And once you do that, you can do like cosine similarity, you can do other vector searches to see what's related to that. You can get a better understanding of the search. So you're not just searching on keywords. You're searching on themes and ideas. Okay? And one way to think about this is if you guys go to the old school library, UNLV's lead library, and sometimes if you don't really understand a topic, you can go to that section of the library. Okay? So just look it up. Hey, Python programming, blah. QR, shelf number 43, whatever. So you walk over to shelf number 43 and you look around and you can find other books related to that. And maybe before Python it talks about algorithms. And maybe after Python it talks about data science or data security or who knows what. But all the books on kind of similar topics are grouped together. So even if you don't know the exact keyword, even if you don't understand the whole library, because you really don't have to understand a library. But if you can just find Python, go to that section of the library where all the Python and programming books are, you can find other cool books. Okay? It's not like there's going to be a romance novel, biology book, medicine book, Python book, I don't know, a history of John Wayne. The books are organized by kind of like this topic idea. They're organized by semantic relationships. Okay, so hey, this book's on this topic, let's put them all together. Where keyword doesn't really work that way. Keyword just says, hey, I'm looking for this keyword, boom, this is what you get. Semantic search is a very different method of diving into what are you searching for semantically. What are you searching for in the larger context of things. It talks about balanced or asymmetrical and symmetrical search. I'm not going to go about too much. Now, I did talk a little bit about prompt engineering, and that's what I should do is make a discussion about prompt guides. Prompting is a new term in the last year or two. Basically, the idea is how you ask an LLM for information greatly affects the results you get. Where it's less in Google. So if you go to Google, and search for something, and somebody else searches for something but kind of changes the words or make it very different, your search results aren't going to be that dramatically different. However, with LLMs or GPTs or BERT, it's completely different. Just changing a few words can dramatically affect the results of your output. Okay? There's a lot of prompting guides, unofficial prompting guides. Hey, how do you find the best resume rewriter? What type this exact phrase in? How do you find the best flights on OpenAI? Type this. And just Google prompting guides or prompting tips or things like this, and you'll find a lot of people that have kind of written up prompts that think they work well. Probably most of them do. Your task as a 20-year veteran of academia is to write a cover letter that's phenomenal. It's so there are certain things that are really good, but in a nutshell, when you write a task, you have to kind of imagine. The only way I can say this is that you have to imagine that you're in a bar and you have a bet with somebody. Okay, and you want to win that bet, so you have to be very clear, you have to be very concise, and be very direct. The more wiggle room or the more nebulous prompt you give it, the more kind of way a person can wiggle out of that bet. They can kind of find a way to skirt out of that bet. They can kind of, I don't want to say cheat, but they'll try to find the shortcut. LLMs are no different. You have to try to be very clear on what you're looking for. Do you want a paragraph? Do you want 150 words? Do you want bullet points? Do you want them to write it as an expert? Do you want to write it as a PhD student? Do you want to write it as a high school student? Be very, very clear on the directions you give ChatGPT. So often when I help people, teachers, and I guess students too, with ChatGPT, that's one of the things, or I guess BERT or Gemini, it doesn't really matter, is that you have to be very specific in what you ask for, more so with a human. So when I talk to you through webcam or in person, you can pick up on tonality, inflections, things like this. ChatGPT cannot do that right now. So instead of picking up on tonations, I have to be over articulate. I have to overemphasize exactly what I want. So if you can kind of understand that, and it's better to have, I don't want to say a long prompt, but it's better to have a longer prompt than a short prompt. I always tend to write a longer prompt than I need to, just to help the machine give it context. So yeah, maybe we'll have like a who can find the best prompting guide. This is an OpenAI one. This is posted up on the web campus. And here's Google's one to enhance prompting engineering. I guess I don't know if they'll even load. Yeah, so there's this one. And this goes in here, providing reference text, write clear instructions. Who's president? Well, again, who's president of what country? So if I was to walk into a bar, me and you were to go to a bar, and you said, hey, who's the president? And I name a president of some country, Vladimir Putin, okay? I could be right. Because you didn't say who's president of the United States. Who is the president right now? You didn't provide me any context. You just said, who's the president? Context is important. Who's president of the United States this year? See, that's what I'm saying about being clear and trying not to allow any wiggle room. Okay? Summarize the meeting notes. How do you want me to summarize them? In Latin? How short do you want me to summarize it? I could summarize notes saying, hey, there's a lot of notes. I'm done. That's not very useful, but it's a summary. So you say, summarize the meeting notes in a single paragraph. Then write a markdown list of the speaker and each of their key points. Much more articulate. Okay? So that's what I'm talking about when I say be clear. And this is a nice little guide, You can test changes. Give the model time to think. We talk about chain of prompt actions here in a little bit. That will kind of come into this. And where's the other one? Here's Google to have a little bit more pictures. It loads. I don't know if this is their official one, but it's just one I found. Know your model's strengths and weaknesses. And this is what I was talking about earlier when I said, hey, kind of know the difference between BERT and GPTs. Know what your model's good at. I, like a dummy, I pay for Claudia, I pay for Gemini, I pay for OpenAI, because each one of those models has separate strengths and separate abilities. I have a truck and a car. If I'm trying to save gas, I'll use a car. If I have to move what somebody asked me to move last week? Somebody asked me to move something last week, and I had to use a truck. So again, it is use the right tools for the right job. Well, use the right LLM for the right process. Okay? Be as specific as possible. Who's the president? Who's the president of the United States currently? And I'll let you read the rest of these. Provide examples, blah, blah, blah. I'm going to talk a little bit about chain of thought prompting. There's some more other things in here, but I think if you can just spend a minute or two to read those, it'll really help you develop your LLM skills. Fine-tuning. We talked a little bit about fine-tuning, but there's two things here I kind of want to mention. So, in a perfect world, you have training set, validation set, and test set. Now, that's probably, out of life, just for me in general, that's probably about a third of the models and the data I see or I work with. Most of the time it's training and test. I don't normally always have a validation set. It just kind of depends on the goal and what I'm doing. So it's not like these are hard, fast rules. Sometimes I don't have anything. They just send me a chunk of data, and I have to split it however I see, however I think is best. So I can do an 80-20 split. I can do a 50-50 split. It's totally up to me. Sometimes people randomly say, hey, here is your training set. Use this as a validation set. And once you get good, we have a test set that we're going to keep private and test you on. So again, it's all kind of different, but as long as you kind of know that a training set is what you basically use to train the machine learning model. So it looks at those things, updates its weights, it goes through and iterates and iterates and iterates. So that's your basic training set. That's what makes its weights. A validation set is you take a small part of that and you make sure that you're not getting basically worse results on your validation set than you do on your training set. If you do, you're overfit. Once you have your kind of model designed and working and optimized, then you can hit it against a test set. Now, a test set in theory, the machine's never seen any of that test set data, okay? And so hopefully its output from the test set is about the same as the training set and the validation set. Then you have a good model. If it's worse, then you don't have a good model, so it's overfit. Now, loss function. A loss function, the easiest way to explain this is something we're always trying to minimize. We're trying to fix. So what is a loss function as a student? Points. We don't want to lose points on homework. We don't want to lose points on the midterm. So we as humans think, hey, I know that I could spend 200 hours doing one homework assignment, and I'd have zero loss. I'd get a perfect score. Or I could spend 100 seconds, let's say, 2 minutes on homework, and I'd probably get, 1 point, and I'd lose 90% of it. So between those two is a scale. Okay? So in 100 seconds, I get basically a zero on my homework. 100 hours, I get a perfect score. So we start at 100 seconds and we go maybe 1,000 seconds. At 1,000 seconds, I get a 50-50 score, 50%. Then maybe in half an hour or 45 minutes, I'm up to a 90%, and that's good enough for me. So a loss function, and like I said, it's really important that you understand a loss function is just a way we try to minimize error. So if you've seen those deep fakes, your loss function is to say, hey, here is the person's face that we have. Here's another person's face. What can I do to basically minimize the changes? What can I do to map A to B to minimize those changes? And don't try to overthink a loss function. A loss function is just a way to say, hey, what can I do to reduce error? It can be in points. It can be in pictures. It can be in words. However it is. A loss function is just a way that a model basically increases accuracy. Now the whole loss function issue is why some people are worried about OpenAI and ChatGPT and machine learning and everything else like that. So the loss function, so if I ask ChatGPT, I would like to minimize car accidents. I want to minimize car accidents for people. It's a lofty goal. Very easy. Nobody likes car accidents. Car accidents are horrible. I've lost friends to car accidents. I want to minimize car accidents. What's the best loss function? I don't know. Kill all the humans. If you kill all the humans, there is no car accidents. Loss function achieved. Perfect score. It's not maybe what we were thinking about, but it is something that a machine could do. Say, hey, look, I noticed in this town we have a higher mortality rate and we have lower accidents. But if I have a higher and higher mortality rate, more and more people are dying, less and less accidents. Well, there we go. So I'm going to optimize death. I'm going to increase death as much as possible in order to minimize, to maximize my loss or to minimize my loss function. That way I can achieve my goal of having very little car accidents by basically eliminating humans. And I know that's an extreme example, but there might be other examples that are a little bit less esoteric, a little bit less out there, that are functionally true. So we always have to be kind of careful when we say, hey, we want to minimize this, and this is kind of what our goal is. So just kind of understand what a loss function is. Chapter 4 goes about how we actually, I think, build a model. Maybe I should have made this a little bit bigger. And this is the idea that the reason I put the waterfall in there is because I never believe anything is as pretty as that until I see it. Okay? So just take a lot of this stuff with a grain of salt. In theory, to do a training or to do some type of process, we collect labeled data, okay, with known outcomes, with categorical values, okay, something we can reference. We select the perfect hypertuning parameters or perfect learning rate, saying, hey, this is how we want to go from A to B. We figure out our loss function, things like this. Okay. Then from there, we do a model adaptation. And there's a couple, there's things in between the two, but basically model adaptation is, we take that pre-trained model and we see if we can fine-tune it on a specific task. Okay, so that's don't let that model adaptation seem kind of crazy. That's just basically taking an existing model and fine-tuning it. Okay, so we have a model, we find some additional data, we find the best hypertuning parameters by testing or by grid search or by a couple different methods. Then we take our old method and we integrate the new data to it, model adaptation. Then did we do a good job or did we do worse? If we did a good job, let's iterate over and over and over again. Can we increase accuracy? Can we make F1 better? Can we do a lot of these things to make life better? Okay. This does have this overall arching, well, let me deploy them all. This overall arching idea is the main goals or the main way we kind of develop models. But remember, any one of these things people can just do their whole life. I mean, hypertuning or hyperparameter tuning. There are people that do that. Nothing else. They don't worry about the data. They don't worry about fine tuning. They just do hypertuning parameters. They do grid search. I mean, that is their realm. There's people that really dig in and look at, hey, what is the best way to evaluate a model? And that's their whole wheelhouse. So a lot of times in bigger companies or bigger models, no one person or no one team is going to do all of this. A lot of times it's distributed, or there's hundreds of people that do this thing. If we're looking at a car and we want to build a better car, it's not like one person is going to go out and grab all the user feedback, all the consumer reports information, for all the information about the current car. Then one person is not going to decide, hey, what's the best way to make the new car to integrate these problems and fix them and put them in the new car. Then one person is not just going to build the whole new car from the old car. There are hundreds of people, thousands of people behind each one of these steps. So kind of keep that in mind. The book really didn't go that. So chain of thought prompting is something that book talked about. And I know last year or the year before, I saw a lot of hacker prompts, a lot of security leaks, a lot of issues with chain of thought prompting. Okay. I think a lot of that has been mitigated and kind of taken care of, at least on Gemini and GPT. I haven't tried it on downloading BERT and running BERT locally. But the idea is, remember in grade school it says show your work? And that's what chain of thought prompting is. Instead of having the machine go from A to Z, we want the machine to maybe go from A, and it's oversimplified, A to M, then M to Z, but we do it under our supervision. And I guess it would make more sense. Let's just dive into it. So the example I did, and this was a couple days ago, so it still should work. Johnny has 5 apples. He buys 8 more apples, and he gives 3 to his friend. How many apples does Johnny have? Johnny now has 10 apples. And that's an oversimplified thing. We could all do that in our head. But that is traditional prompting. You just give it all the information and let it solve it. But when you do chain of thought prompting, let's think through the problem step by step. Johnny starts with 5 apples. He buys 8 more, so we add those to the initial amount. After buying more apples, he decides to give 3 to his friend, Richard, we can say that. To find out how many apples Johnny has in the end, we need to subtract the apples he's given away from the total after he buys more. Let's calculate this out step by step. Johnny has 5 apples. He buys he buys 8 more apples, bringing the total to 13 apples. After that, Johnny gives 3 apples to his cool friends, and we subtract those. 13 minus 3 is 10. Johnny has 10 apples. Same answer, but the difference is one, we have explainability. And this is a huge issue in particularly the medical realm. Okay, so doctors, for the most part, do not like AI in its current instance. Why don't doctors like AI in its current instance? Because doctors right now in AI does that first one. Your patient has rheumatoid arthritis. Your patient has sepsis. And as a doctor, you want to know, why are you thinking that? What is your chain of thought to show me that my patient has this? Currently, in most medical EMRs and most medical AIs, I should say that, it doesn't show that chain of prompt. It doesn't show that explainability. Most AIs do not really, people don't want it. That's another reason why. It's not necessarily a technical issue, it's that people don't want winded explanation. But having that explainability helps dramatically both the model and the human, because now if something is wrong, you can figure out what step something is wrong at. You know, if I was to say my patient has sepsis, and it just says your patient has sepsis, and whatever, he doesn't have sepsis, he's just fine. And I said, hey, can you explain, machine, why you think the patient has sepsis? Okay, that looks good, that looks good. Oh, whoa. Number 3, I think the machine pulled the wrong X-ray, or I think the machine misread something, or you type back to the machine, no, number 3 is not correct. He didn't give 3 apples. The patient didn't get hit by a car. Oh, and the machine can update its model. So this chain of thought prompting is very vital, and I'd like you to just try a couple random chain of thought prompts to learn how it works. Because again, I think in the future, explainability, explainable AI is going to be a really, really vital point to AI. Instead of just giving me the right answer, I want to know how you took me down this road. Sorry, I'm speaking so much on this. I just think it's really vital that chain of thought prompting becomes more standard and we use it more. So I have 2 GPTs that I use for coding. Okay, I have one that says you don't know Jack, and it's a smart but Python, I guess, GPT that helps me code. And for that GPT, I specifically said, don't basically talk to me, give me sarcastic answers, and give me, tell me the problem and just move on. I don't care. I just want the answer. I want as minimal interactions. Show me the code and just give me what I need. So that's one of my GPTs. Okay, I have another GPT that I use that says, hey, when I encounter an error, let's go through it step by step to figure out where I'm not understanding. Why am I here? Okay, so I have 2 different GPTs. One is my get things done. Just basically, it's a smart but GPT that just tells me I'm an idiot and do this. Okay. Then I have another GPT that I trained that basically kind of give me a chain of thought. Say, okay, you did this is correct, but here's where you have a typo, or here's where you have an incorrect version of NumPy, or here you have an incorrect version of Pandas, or here, your array is not set right. Your data frame is wrong. And it takes me step by step of how it debugs some of my code so I can learn how to decode better. Okay, and I think this is very vital for everyone to understand. So that's that. The book also talks about image prompts. This is just some stock image I have, I grabbed. So I uploaded it and said, hey, can you describe the picture? I kept it super simple, a super simple picture. The picture shows a roll of US dollar bills bound by a rubber band. Blah, blah, blah. The bills are curled up. Nobody cares. Okay, so there is a few different ways that this can happen. I had to look really quick because I didn't think I put them on there. So there's a vision transformers. I think. I'm wondering if one of my extra credit papers is on the vision transformers. But anyways, so a vision transformers, which I've only used a few times. But basically, image is divided into chunks or patches, I guess 16 by 16 patches. I don't know what size. I think they're 16 by 16, 32 by 32. And it looks at these kind of patches and seeing how they relate to each other. Okay, so that is kind of like a jigsaw puzzle. more than anything else. Whenever I think of vision transformers, that's always what I think of. Another one, much more common, but maybe not as common, maybe not as growing as much as vision transformers, is CNN, convolutional neural networks. So CNNs, you'll see pictures on the internet. One second, let's see if I can find one. Okay, here's not the best one, but here's at least, oops, oh, darn it, right here. Okay, so a CNN will look at the image and say, hey, I'm starting to notice things like this. Okay, here's actually a better one. Okay, so what does it notice? Well, this car has a line right here. Here's two circles. So I know things that maybe have two circles, or either a motorcycle or a car. So you see there's a circle, oh, there's a wheel hub. Okay, so, and I know it's hard to see. I guess that's the best you can get. So basically a CNN kind of starts matching patterns. Oh, here's a line, here's a line, here's this. We can see lines here. We can see feature extractions here. Here's a line. Here's a line. Then it goes to maybe circles. Here's a circle. Here's a circle. It starts finding these patterns. Then it basically builds upon those. Okay, so that's how CNNs work. They do it by color. They do it by edges. They do it by patterns. And they kind of match those patterns. Okay, so basically what we do is we upload an image. It kind of breaks out the patterns. Then the model, the AI model uses its patterns to recognize objects within the image. Now, there are models that extract context from images. So it says, hey, here's a stop sign. Here is a horse. Here's a car. Here's a sidewalk. Here is a moon. Okay, so there's one way to do that. There's models that basically put out those keywords. There's also other models that basically literally put out vectors or patterns. Okay. So, in the end of the day, it doesn't really matter, because at the end of the day, what you're really looking for when you upload an image is features. What features does that image have? Okay, because the features are the semantic context and vocabulary. So if you're looking for a sentence that has no meaning, you don't care. It is fun out. That's useless. It has no context. It has nothing. If I was to put a question on your midterm, it is fun out, and then just give you 4 random choices. The sky is blue, the earth is flat, Las Vegas has 20 trillion people. How would you answer that? You couldn't, because there is no context, and it is fun out. You need context. You need semantic information. Same thing with images. Images, we need to find features. We need to find lines, we need to find circles, we need to find things that we can recognize. We need to find these features. Once we find these features, we see what these features are related to. If I had 1, 2, 3 circles with 2 circles below it, that could be the Olympics. If I had a circle that kind of had bented lines and it was red and has some text on it, STOP, it's a stop sign. Okay? So there are differences between vision transformers and CNNs on how they actually do this. But at the end of the day, we want to understand the features in that image. Once we understand the features and kind of what is in the image, the nice thing is we can process those features through an LLM and kind of generate a description, generate more meaning. It is more likely that a human will hold a $100 bill than a monkey to hold a $100 bill. Now, not that a monkey can't hold a $100 bill, it's just more unlikely, less likely. So that's how we also run it through an LLM, and the LLM kind of helps us add another layer of meaning to that picture. So I think, do I have any more? No, okay, so that's it for the didactic part. 48 minutes. I went a little slow because I wanted you guys to really get a good general understanding of this. And we haven't had one of these high-level talks in a while. So hopefully that does help. Don't worry about anything, like I said, that you learn. I just want you to really understand the 10,000-foot overview. I want you to Google and read. If I ask you, hey, why is an embedding... What's the difference between an embedding and a CNN? Or what is the difference between word-to-vec and a token? These are things you should be able to answer off the top of your head. I'm not going to ask you, hey, what's the 3 different types? What's an optimizer for a CNN? You know, what's the difference between an atom optimizer and a gradient optimizer? Nobody cares about that right now. I want you to understand what a loss function is and why it's important. So now the homework, 2 to 3, 4 homeworks, I don't know. So you have a draft BERT topic analysis. So basically, as long as you can show that, hey, you can load a data set into a notebook and you can try to apply BERT topic, you get perfect points on that, okay? I'm going to be very general with that one. That part of the homework is just to kind of say, hey, this is kind of what I'm looking for, or what you're looking for to me. This is kind of what, you know, here's my data set. It's Twitter, or it's Chat GPT prompts, or it's, you know, something. So there's your data set, and here's what I kind of want to do on BERT. Okay, so that's part 1 of the homework. That's due on 2 days from now, on the 6th, okay? And like I said, if it doesn't work, that's fine. The goal of that is just to get the data set and kind of start figuring out what you want to do with BERT. If it works, great. You know, that's great. So that's just part 1. Part 2, due on the Monday, I think, or the Sunday after spring break, I believe that is. I might have to push that back a day. But basically, it's due right at the end of spring break or the beginning when we come back. So, same as part 1. But now I just want BERT to actually work, BERT topic to actually work. Where it didn't have to work in part 1, but I actually want it to work. I want it to do something. I want to find some topics. And then just give me a pretty picture, George. Just a visualization. BERT topic is really good at giving a visualization. As long as the visualization is kind of relevant to what you're trying to show me, I'm happy. There's a ton of different visualizations in BERT topic. Just pick one that you can get to work. Don't kill yourself over it. So if you have a data set, BERT topic, hacks on it for a while, find some topics, you give them a visualization, your homework's done. You know, you can do, if you did all that in like 15 minutes for some reason, you're a programming genius, you can submit it to part 1 and part 2. I don't care. That works for me. But I just want you to understand the difference between part 1 and part 2. Part 1 is just a draft. Part 2 is actually functional working. If you happen to get lucky and get everything functionally working, submit the same thing for part 1 and part 2. That's fine. I made a video on the midterm. Don't stress out on the midterm. It's not that hard. Everyone's going to do fine. There's 2 parts to the midterm. I think you can take it 5 times. Part 1's all the multiple choice questions. Part 2 is like short answer, like 2 short answers, like what is vectors and how is NLP or sediment analysis important for business. But since part 2 is fill in the blank, like a short writing, like a paragraph or 2, if I put it in part 1, anytime you had to retake it, you'd have to re-upload it, and that's a nightmare. So you can take it up to 5 times, both of them up to 5 times. You can Google the answer. You can use notes. You can use Chat GPT. I don't care. The only thing you're not allowed to do is get help from somebody else. You're not allowed to share your answer with anybody else, and there's a few other caveats, but you basically have to do it on your own. There's a video I encourage you to watch on the midterm section. So when you go to take the midterm, there should be a little video. It explains all the rules, and it even gives you like some questions and answers and everything, so you should all be fine on that. We covered this before, so that's it. Let me just pull up a calendar, 2024. Okay, so that way we can level set. Okay, so this is where we're at now, 3-4. So you can do the midterm this week, you can do that lecture, this lecture I just talked about, I don't care. Next week is spring break. So in theory you're off next week, but you know, I'm not going to give you an assignment. Focus on your other classes, play catch up. I'm going to catch up on all grades. This is when that final homework's due. So, you know, if you turn in the part 1 of BERT, I'm hoping to get it graded and back to you by Friday or Saturday here. Then, you know, spend a day or 2 here working on it, spend a day or 2 here working on it, but submit your final one there. Okay, we'll get back into transformers this week. So actually here, let me go over this way. Let me look right here. Week by week plan right here. Okay, so this is where we're at right now, the midterm, and like large language models. Like I said, they're interchangeable. I don't care what order you do things in. Then when we get back, you know, we're not going to do this book, so don't worry about that. Did I really cover latex? Oh, well. From now on, we're just going to try to do transformer, open face, and I'm going to give you hopefully a lot more freedom to do the assignments in the way and manner you want. I'm going to focus mostly on the goal, not the data, not the process, not necessarily the technique. I'm going to explain, hey, here's how you fine tune a model. So here is a model A, fine tune it however you want to fine tune it, that's fine. I want to generate text. So maybe you want to generate non-English text, or maybe you want to go from English to Spanish, or maybe you want to go from a 5th grade level to a PhD level. However you want to do it, will be a lot more freedom. But most of this is going to be all Hugging Face. Most of this is all going to be the transformer type models until we get down to here, which is going to be pictures and videos, like multimodal or sound, audio, DAX, things like that. So. But on that, everyone's doing great. Have a great spring break. Feel free to email me, text me. I'm here to help you. If you guys want to meet up, let me know. If you want to meet on Zoom, let me know. I'm on campus on Wednesdays and Fridays. So I'm here to help you succeed. And good luck with all your other finals. Thank you.